Okay, so now, as I mentioned from the previous video, we have a simpler technique to compute the surface integral, where the surface is a closed surface, where we have a solid, where the boundary of that solid is from the closed surface. Okay, so in order for you to apply that method, we use or we implement the Gauss theorem. So the Gauss theorem is a theorem which establishes the relationship between a surface integral, this one is a surface integral, and a triple integral. Okay, for the surface integral, over the surface sigma, where the surface sigma becomes the boundary of the solid. Okay, and the triple integral on the right is a triple integral, or the what we call that, the volume integral, because we have a dv here, the volume integral for the divergence of the vector field f. You can see we have the similar f here. Okay, so the amount, the value that you can have from the left is similar to the value on the right side. So in this case, this formula is called as a Gauss theorem, or sometimes people say that this is divergence theorem, because as you can see here from the formula, there is a formula of a divergence. So do you remember last time about in chapter 4 we have the gradient, the application of the gradient, we can evaluate the divergence of the vector field and also the curl of the vector field. So in Gauss theorem, we apply the divergence of the vector field, where this one is related to the whether the vector field, I mean the fluid. Let's say we have the fluid flow. We know that the fluid flow is represented by a vector form, in a vector form, right? So that particular fluid flow or fluid is compressible, or what we call that, incompressible or compressible. Okay, yeah, something like that. Okay, so about the diverge or converge. So, or if you remember, we have a sink point, we have a source point. Do you remember that? If we something, let's say, sorry, you have last time we want to evaluate the divergence of the vector field. If we have it can be positive, it can be positive, it can be negative, it can be zero. Okay, so if the answer here, if your divergence grad dot f is 0, then you can see that the flow, the vector field or the fluid flow is incompressible. Okay, incompressible. Okay, but if it is positive and if it is negative, it can be a source of sink. Okay, let me show you again about that thing. So this one, divergent, if the answer at that point, if the answer is positive, meaning that the flow, it is something diverge away from the source point. Okay, so that is called a source point, which is away from the point that we have. But if the divergence is negative, if you compute the divergence here and you got negative, so meaning that it is converge. In this case, we have a sink point. Okay, and then if the divergence is 0, where your value here is 0, so then your flux, I mean your total expansion or compression, I mean or all these values if the integrand 0, so all the values here 0. Okay, so meaning that if your vector field given is incompressible, so that then the divergence of course 0, right? That is the property of the incompressible, where the divergence of the given vector field is 0. So meaning that it is not diverge, or it is not converging. Okay, so the flow of the gas or the fluid is in the same direction. Okay, so now we extend our understanding on the divergence. So we implement that in the Gauss theorem. Okay, so the thing that we have done previously, we have already calculated this one, right? So we have the F dot capital N dA and so on. But now let's say we have the closed surface where it becomes the boundary of a solid. So we can simplify our calculation using the right side, because we know that, for example, as we done on the previous example, you have calculate the sphere. Okay, where the sphere here is the we have a complete sphere. So and the surface of this is a closed, which is that surfaces. So you got two surfaces. They are become the boundary of the solid sphere. Okay, so we can, instead of we calculate this instead of we calculate that twice, so I mean you have to consider the positive z and the negative z, and then you have to provide you have to calculate twice for the surface integral. So we just evaluate only one, but you have to use the formula on the right, where you have to deal with the triple integral, and you have to evaluate the integrand here is the given by the divergence of f. Okay, just this one normally is more simpler than you have to compute for all the surfaces that you have from if you are using the left method. Okay, so now what is the physical meaning? So I explained a little bit on the physical meaning of this. Okay, imagine that you have I'm using the same sphere here. Okay, imagine that this is a ball. Okay, and you fill up this ball with gas, but with the condition that you have to assume the ball is rigid, which is once you put the gas inside, so the size of the ball does not change. So if you can imagine that if you put as much as gases in the ball, so what happened to the gas inside? Because you said that we have to assume the ball cannot be becomes larger. Okay, so the gas inside the ball is compressed, right? Compressed. Okay, so now the physical meaning of the triple integral, now I just rewrite this to get you around, but the idea is the same. So now the idea of the triple integral, this one is actually telling you the total expansion when you put the gas inside the ball. So whether the fluid becomes expanding or expansion, or the gas here becomes compression. Okay, I mean becomes compressed. So can be either, it depends on the f that given to you. Just because of how can we have the word expand and compress? Because of we have the value of divergence here, depends on the f that you have. So if the value here is positive, so it looks like it is become expansion, diverge, right? Because you have a source point and it becomes diverge. But if your divergence here negative, so the gas here becomes compressed. Okay, or you call that as a compression. So the left side here telling you the total expansion or total compression of the fluid the fluid here is given by the vector form F, okay, where the fluid or the gas flow inside the solid that you have, because we know that how can we relate the solid and the closed surface. So this one is specifically for closed surface only, not open surface. Okay, so the closed surface here becomes the boundary of the solid, this one. Okay, so now what is the physical meaning for the right side? As I mentioned before, the surface integral of the fluid F over the surface here. Now you have a closed surface, so closed surface here, because it is closed, then we can assume this one is just like a solid. So the right side here telling you that the total flux, okay, the total flux of the fluid, so here the blue arrow here is the fluid flow or the gas flow out of the boundary of the solid G. So the value of the total expansion and the value of the total flux, they are the same. So this is the idea of the Gauss theorem. Alright, so meaning that the value here can be negative and also can be positive and also can be zero, because if your divergence here is 0, so your flux is 0. Okay, so that is the idea of Gauss theorem. Okay, now we want to apply the same problem as we done previously here, using the same problem that we discussed from the previous video, but you have compute that using surface integral, right? But you have to provide sigma 1 and sigma 2, and then you have to total them up, right? So you can see here how long they are, how long you have to provide the step, which is, it is of course unique sometimes compared if you just use the triple integral. So now we implement the Gauss theorem to solve this problem. Okay, so when we look at this example, okay, so the same as a 5.15. So we have the sphere with radius A. So let's say this one, A, and A. Okay, so we want to compute the surface integral where the surface is closed surface, which is becomes the boundary of the sphere, F dot N. Yes. So now we want to implement the Gauss theorem, where you need to apply the triple integral and divergence of the vector given dV, solid G. Okay. So firstly, you have to evaluate the grade dot F. Okay. So then what is a gradient? Del x. So if you don't remember, then you have to do it one by one. Del y, del z, and dot with f. F in this case is given by 0, 0, z. So when you implement, you apply the dot product. So del x 0, 0 plus del y 0, 0 plus del z. Del z of z will give you 1. So now your gradient, your divergence is 1, positive. Okay, so now we plug in to the formula using the Gauss. You have 1 dVg. So in this case, if you relate this to the triple integral that you have learned before this, so when you have 1 dV, so actually you are computing the volume, right? But it's not necessarily a volume, depends on the the divergence that you obtain. Okay, so now we have to decide what is the how can we solve this. So based on your solid, we have a sphere, so it looks like the most appropriate the most convenient coordinate system we have to apply here is spherical coordinate, right? So now we apply the coordinate spherical. So 1, so dv is rho square sine phi d rho d phi d theta. So theta 0 to 2 pi, phi, because you have a sphere, complete sphere, so 0 to pi, and then rho is 0 to a. Then we want to solve, so we integrate respect to rho. So you got sine phi is constant, so rho cube over 3, and then replace the limit 0 to a d phi d theta. So then you will get a over 3, a cube over 3. Okay, and then integrate for sine, will give you negative cos phi. So 0 to pi d theta. Okay, so then I just put the negative outside, and then cos pi minus cos 0, and then I integrate 1 d theta, so give us theta and replace the limit. So cos pi is minus 1, cos 0 is 1, so negative 1, negative 1. So minus 2, you got minus 4, and negative, so the negative gone. So this is the answer. And then now we can only have a few steps here, only this one. Compared with if you apply the previous technique where you need to calculate, now you can see how long they are, right? And at the end will give you a similar answer. So now we already obtained that the calculation from the left side, this is from the Gauss Theorem, the calculation from the surface integral, which is this one, is similar to the calculation using the triple integral. This is only, remember, this is only applicable for closed surface. If you have closed surface and they ask for finding the surface integral, then you can use this Gauss theorem. Otherwise, you have to use the as a previous method. Okay. Maybe sometimes in the question they will ask you to evaluate. For example, you are given a surface. Maybe they give you. Okay, let's say I give you a cuboid. Again, cuboid. Where the size of the length, the width, and the height, they are not the same. So it's cuboid. Y, Z. It looks like it is closed, right? But then they will ask you evaluate the surface integral for the 5 surfaces. We know that the total surfaces of the cube or cuboid, there are 6, right? Let's say they will say evaluate the surface integral for the 5 surfaces except, okay, or I will say compute all the compute the surface integral for all of the surfaces of this cube or cuboid except, let's say I give a plane A, B, C, D, except the plane, except this one. Okay, so meaning that you have to compute the surface integral for this side. You have to provide me 5. You have to provide me 5 surfaces or 5 calculations. But you cannot use a Gauss because this is not closed. Okay. So that is the idea about the Gauss. The condition to apply the Gauss is it should be closed. Okay. Or instead of you compute the whole 5 surfaces, where you have to provide me 5 different kind of surface integral, or you can evaluate the whole surfaces, which is using the Gauss theorem. I mean, all over the cube or the cuboid using Gauss theorem and minus. Okay, and then you compute the whole, and you compute the line integral for the A, B, C, D plane, and then you just subtract them. You understand? You compute the whole cuboid using the Stokes theorem, using triple integral divergent f dv for this cube or cuboid, minus the surface integral for the plane of this still considered as a surface line, but this is open surface for A, B, C, D. So you have to compute double integral f dot n dA over the region R. So this is another trick. Instead of you provide me all the five surfaces, which for me there is something you need longer time, right? So this is another way. I think this one is more simpler because of you have a Gauss here. Okay, that is possible. All right, so that is an example of the Gauss. So any other example here? Okay, look at another example, 5.17. So in this question, let the surface let the sigma here is the surface of cylinder given by this equation, bounded by all the wall and the floor, and also z equal to 4 in the first octant. So you have to highlight this. This is very important. First octant only. Okay, and the vector field is given, and you have to evaluate the surface integral. So now we want to check whether we have a closed or not. We have a closed surface or not. So then you have to sketch. Okay, I'm sure that you have no problem in sketching this. Just to take precautions, so list down all the information provided, otherwise maybe it is easy for you to get wrong in sketching them. So you have the planes and also the curve, the surface given by x squared plus y squared equal to 4. Sorry. So it is actually part of a cylinder, right? And since we only interested on the sketching in the first octant, then we only have this one. So since we have only this two variable, total variable is 2, then there is only one trace. So we do a projection. Remember I teach you before. So we have this particular shape, and it looks like open, right? But then since they said that the surface is part of a cylinder bounded by the planes z0 is the floor, x0 is the wall over here, and y0 is another wall, and z equal to 4. So this one should be z equal to 4. So it looks like we have a closed surface. We have a solid where the solid is covered by the surfaces. So let's count how many surfaces that we have. So the surface that we have, so let's say the left wall, number 1, the right wall, the front wall, that is number 2, and the floor, number 3, and the roof here, number 4, and this one, okay, if you can see that is number 5. So we have 5 surfaces, and it is closed. Okay, in this case, the thing that I want to show you here is only using Gauss. because as we know that we can use the Gauss Theorem. Why? Because we have a closed surfaces where it is a solid actually. So now we want to solve this using Gauss Theorem. Actually, the question here asking for both direct, mean you have to provide 5 surface integral. This called directly, but I don't want to do that. Okay, here I just want to use the Gauss Theorem because I want to show you how we can use Gauss. So using Gauss, we have to apply triple integral, and you have to find the divergence F dv, solid G. So now we compute for the divergence. Okay, so we have del x of okay, your F, where the F given is x 2 and then z squared. Okay, so del x of x plus del y of 2 plus del z of z squared. Okay, so we have 1 plus 0 plus 2 z. So what we got here, we have 1 plus 2z in dv. So that is our integrand. Okay, so normally when you calculate the gradient f, the grad dot f, we don't bother about the value. So we just provide the dot product between them. Sometimes you can get constant, sometimes you can get an expression in terms of z, or in terms of y, or in terms of z, or can be a mix of them. Okay. So now about the limit. Okay. So if this is your solid, so now we go back to the triple integral that you have learned before this. So what kind of you have to decide what the orientation, I mean the way you're standing inside the solid. So where normally we choose this, we write this orientation. So we know that this is called your region, or some of you call it as a shadow. So your shadow is when you're standing like this, so your region should be on xy plane. So we call that is xy solid. Why we need this? Because it will guide us to determine the order of integration, which means that your dv is dz, dA your region on xy plane. Okay, so now we can determine the limit of z from the solid. So your lower bound is z equal to 0 and your upper bound is z4. Okay, so now we got the limit of z. Okay, so now when we are talking about the region, so once you normally when you obtain the sketching, you must provide the trace, right? So as you can see here, the trace is coming from xy plane, where this one. So this becomes your region. So that is your R. And then if you look at here, you can use Cartesian, or since this one, if you look at from the original equation for the cylinder here, we got a circle, right? So which means that your region is a circular region. Okay, so when you have a circular region, so then you have to determine your I mean you can use polar for 2D, but now we are using 3D, so we call this cylindrical coordinate. So from your region here, we know that the circle is radius 2, so 0 to 2. How can we determine that? So you draw a line passing through the origin, and they are all from the similar lower bound and end up on the similar upper bound. So we have 0 to 2. And then theta, since this one is only located on the first octant, so it should be 0 to pi over 2. So we got the limit, all of them. So in this case, we want to solve using triple. So 1 plus 2z dz, and then you have r, dr d theta, 0 to pi over 2, r 0 to 2, and then your z just now 0 to 4. Okay, so now it looks like I'm sure that there is no problem for us to integrate this. Okay, so that is the answer when you integrate them. This is not so complicated, just be careful when you integrate.